All right, so here we go. Okay, so today we're going to do that problem about to find the shear flows in that wing box section, okay, or wing spar, whatever you want to call it. And also we're going to try to find the deflection. So example, here this should be page 101. So in here, basically, we have a wing box structure, or wing spar, whatever you want to call it. Okay, so let's see. All right, so we know it's clamp over here. All right. I personally consider force to be applying here because it's a member. So let's call this one V, and we know that V is equal to 44,500 newtons, so 44,500. All right. And that the overall length is 2,000 millimeters. Okay, so dimensions will be in millimeters. So here we have the booms. And let's do a numbering. 1, 2, 3, 4, 5, and 6. Okay. I don't want to put too much information on the same figure, so let me do quick another figure here. One, 2, 3, 4, 5, 6. And we know that the height is 250 millimeters. This one over here is going to be 250 as well. And this one over here is 500. Okay, so the question over here is to determine the vertical deflection at point 2. Okay, and I need to add over here that the thickness of all the panels T is 2 millimeters. Okay, so let's first write down the main equation we need to use, okay? And then we can figure out what we need. So the deformation at point 2 is given by Castigliano's theorem, that basically we take the strain energy and we need to differentiate with respect to the force or at the location. So remember, we call Q. So we find the Q at point 2. So in this case, let's use your common sense. If you have the force over here, this is going to bend up, no? And the bending up, the deformation is mainly going to be due to what? To the bending moment, okay? All right? So the deformation due to the bending moment was equal to what? It's equal to deformation 0 to L of M over EI partial M. And here what is important is that remember that in Castigliano's, in order to find the deformation at the point here, you need to have a force applied at that point, no? So is it a force applied at that point here? Yeah, so we need to take the partial derivative with respect to V. And this will be dz, because I think the reference frame here is X, Y, and Z. Okay? So this will be the effect of the bending moment, but then since this one is not symmetric, what's going to happen? This structure here is going to twist, no? So the twist of the deformation due to the shear flows is also going to produce some type of deflection. Does that make sense? Okay. If this one moves up, it will be no effect of the torsion, but because this is probably going to twist now, the twist is also going to affect the deformation. So, and that term over here is the most complicated. So we had one that was 0 to L, the length, and then one that we needed to do around the cross section. And I think that one is equal to Q, partial V. So this will be across the cross section, and then dz. Okay, so this is bending due to moment M, and we're going to calculate what this moment is, and this will be bending due to shear, but really this will be, if you want, due to torsion. Okay, so let's find what we can now. So let's solve for, let's find M and maybe I. Okay. So now it's back to statics. I need one more color here just in case. All right, so the bending moment, what do we have? If I do a sketch to find bending moment, basically if I do a 1D sketch of our wind box, what we have is this. Here. Let's say this is Z and this is 0, 2000. Okay, so what would be the figure of the bending moment here? So I mean, if you do the bending moment, how will it look like? Where is the moment maximum? It will be at the root, no? What will be the moment at the free end? It would be 0, no? Okay, so if we do it, we'll have some type of straight line this way, okay? So I mean, we can do the equations, but we can do it pretty quick. Could do the summation of moments, make the cut and everything, but I think we can do it pretty quick here. Or M will be equal to what? Should be equal to V, but now we know that it needs to be equal to 0 at 2000, no? So what can we do? Z, because this is the length, minus 2000. So this will mean that when Z is equal to 0, the bending moment will be equal to Vz, no? Will be equal to V times 2000, correct? Which is the value of the moment. Yeah? And as we move, this one will go down to 0. Okay? So this is basically the equation of this line. All right. So good. We got that one from the first equation. For this one. So we got M. E is a material property that maybe I forgot to give. Is it given in the problem? Oh, yeah. So let's go back over here because I forgot to give you a bunch of stuff. Sorry. So in this problem, we have, go back to this page. We know that E, the Young's modulus, is equal to 69,000 newtons millimeter square. The modulus for rigidity for torsion is 25,900 Newton millimeter square. Then we know the areas over here, B1 equals B3 equals B4 equals B6 equal to 650 millimeter square, and B2 equal B5 equal to 1300 millimeter square. Okay, so we almost have everything to determine the first term. We need just the I, okay? All right, so let us here, assuming that shear, panels / skin / webs are non-effective in bending, which is what we have been calling case 1. What do we have? We have that I, this is bending about which axis? Will be about the x-axis, no? Okay, this would be ixx would be equal, we know, of y squared dA. This is the general equation. But once we discretize or idealize the structure, this is equal to the summation of the y sub I squared times b sub r. Okay, so over here, if we look at our structure on top, so let's just do it over here very quick. Okay, so what we're gonna have is 1, 2, 3, 4, 5, 6. This will be our natural axis. This will be the origin of our y. Okay. And I'm not going to write the value. So what? But we will have what? Ixx. So we know that 1, 3, 4, and 6 are equal. Okay. So we can do 4 times. So it will be for 1, 3, 4, and 6. So 4 times. What would be B1, B3, B4, B6? They are 650. So I'm just going to do it now. This is millimeter square times y, which is the distance to the natural axis. So that distance to the natural axis will be what? The height is 250. So this is 250. This should be either plus or minus 250 divided by 2, which is 125 millimeter square. And okay, so I started working on the MATLAB, but we're going to modify it together. So you see, this is the problem I started working yesterday. So I think I started doing this one. So these are the dimensions. Here I did, this is what we want to do. I also did case 2 yesterday. So let's run it up to here and see what we get. Where do I run it here? Here, I don't like this screen. I wish I could put it separately, but let's go all the way up. So 1, 2, 3, 4, 5, 6. So 1, 2. So it looks like it's 81.25. Ten to the 6 millimeters to the 4th. So let me go back here. There we go. Oh yeah, I forgot. Yes. Yeah, the same thing that happened on the previous problem. Yeah, correct. So what I forgot here, the result is going to be correct. But here, what do we need? Plus 2 times the 1300 millimeter square plus minus 125 millimeter, everything squared. Okay, but the result would be the same because when I did in the MATLAB, I think it's doing the summation of all of them, no? See, there's B, B1, B2 times the Y. Okay? So 81.25. All right, so now we could almost do everything of this term over here. So if you want, we could do this term and then, or let's do everything first and then we do the deflection, okay? So we have M, we have E, we have I, we know the M in function of V, no? Yeah, so let's do it. Otherwise, since we have everything, let's just do it. We could wait until the end. So let's just say that, and this is going to be the main factor. The other one should be very small compared to this one. Let's do 103. So let's say the deformation due to bending can now be determined. Okay, so let's say this will be Q2 bending, I call it this way, is equal to the integral of M over EI partial M partial V dz, and this is along the whole length of the beam. Okay, so we know that M is equal to V Z minus 2000. We know I is equal, we just calculate equal to 81.25 10 to the 6, and E, just copied before, is equal to 69,000. All right. So with that information, what would be the bending, the deflection due to the bending? What is M? Is V, let's say V over EI. So M is V of Z minus 2000. Now, what would be the partial of M with respect to V? The V will disappear, no? So we just have Z minus 2000, no? Yeah? Divided by EI, and now we need to integrate this with respect to Z. So basically, this is going to give us Q2 bending equal to V over EI integral 0 to 2000, because it's L of Z minus 2000 square dz. Okay, so I actually did that calculation on the MATLAB. I mean, we can do it by hand. It's not complicated, but so you see on the MATLAB, this is the M, what I have over here. This is the dmdv Z minus L, and this is the EI, no? So this is exactly the same expression. All right? So when I go down, this is the deformation. How do I call this one? Deformation M. So I think I'm pretty sure it's this one here. So we do that, we get 21.17 millimeters. Okay? 21.17 millimeters. But I mean, again, if you want to integrate this, what would that be? Will be z cubed over 3 minus 1000 z plus the double product, no? But anyway, so from MATLAB, Q2 to bending is equal to 21.17. millimeter. Okay, so in most cases, to tell the truth, this should be sufficient because you agree that if you have this structure, the main deformation is just going to be due to this force pulling up, no? The one due to the twist, it should have some effect, but it should be minimum compared to this one going up, okay? All right, so we have page 101, 103. So now we need to find the second term, which will be this one over here. So in order to be able to apply this equation, what do we need to find? We need to find the different shear flows to determine this term over here. We need to determine the different shear flows across the cross-section. All right? And here is good because this cross-section is uniform. So basically, there is no taper on the x direction or the y direction or the z direction. All right? So what does that mean that about the shear? Remember, if we had to do the figure of the shear, the equivalent figure to this one, what would be the, remember you can do the shear force and the bending moment, no? So what would be the shear force diagram? So we do, let's say, the shear diagram. If we had to do the shear diagram, I hope you remember this stuff. This is V. Let's say this is Z, which is between 0 and 2000. What should be the shear diagram? Okay? It would just be constant throughout the whole length, no? Okay? So the shear force is the same one. So that implies what? That the shear flow at any cross section, any place along this beam is going to be the same. All right? Again, I hope you don't have a problem in finding this curve and this one, no? And this one. I mean, you will do that if you want. I'm not going to do it on paper, but what would you do? You will take your beam. I'm going to do here some type of very quick. If this is your problem, you have this. You have your force V, no? If you want to use from here, Johnny, what will you have to do? You will have to say that here you have your force V. Here you're going to have a reaction R, let's say RY. Rx here will be anyway 0, and here we'll have a bending moment at the root, no? Okay? You find this by doing summation of forces, summation of moments, and then you take here and you need to make a cut to make the external forces to become internal. Sorry, to make the internal forces become external. This will be V here. This will be the bending moment. This force Ry will be equal to what? To the value of the force over here, no? So you want this will be, really this should be, Ry should be minus V in that direction. So you see that the V should be equal to V over here, no? Ry, and the bending moment will be equal to what? V times Z, okay? All right, I mean, but I'm not going to do it in detail. This is statics. All right, so that means that because this is constant, the shear flows are constant throughout the length of the, I'm going to call it wing box, but it can be wing spar as well, okay? Whatever you want to call it. Okay, so now what do we need to do? We need to do the general procedure, which is what? We have here. So what are we going to do? We're first going to make two cuts, because if the cross section is closed, we don't know where to start. So we need to open the section. All right. And then so we do the cuts here. So this will be Q equals 0 over here. And then we can do the Q1, Q2, okay? And I think we call this, I don't remember, Q bar, I think. This will be the Qs. Plus one of the Q1 or 2 due to the torsion. Okay, so this is the general procedure, no, that we needed to do. Okay, so first thing we're going to do is this term over here. So we make the cuts. So let's see, how's the numbering? 1, 2, 3, 4, 5, 6. Okay, so from this figure, let us start by, really should be, let's say we start by cell 1. Which is, for the name I call, should be this one over here. Okay? So we start from the cut. So what do we know? Q 2, 3 will be 0. All right? Now, okay. So we have this, Q23 will be 0. Now we go to Q34. So Q34 will be equal to what? Q23 minus Vy over I over V, not Vy. Is V times Y, but V divided by Ixx times Y of what? Should be Y of 3, no? The first one. So we know this is 1, 2, 3, 4, 5, 6. And we know this is 250. Okay? So let's do the first one by hand if you want. So this one should be equal to what? 0 minus V is equal to 44,500 divided by IXX, which is equal to 81.25 10 to the 6 times Y, which will be what? 125, no? Positive 125 because it's on top. Times positive 125. By the area, no? Yeah, so you see. So it's V times B3 Y sub 3, so I forgot the B, and this will be, so it will be the Y, the B, so B3 is 650, no? If I remember properly. So that's good. Thank you. So do this calculation with your calculator, but if we didn't do anything wrong, this will mean that Q34 is equal to negative. So we look at the MATLAB. I mean, I'm gonna have to modify later on. I think here is everything is about the same. So I come here, this is just the area. So you see Q23 is equal to 0. Q23 minus Vy Ixx B3 Y3. So Q34, if I go here on top, should give you minus 44.5. And I think you all found that, okay? So minus 44.5. Okay, and the units of this should be newtons per millimeter, but I don't have space, so we'll just leave it as this one over here, okay? So similarly, what we're gonna have, we're not gonna do as much detail, but we'll have what? Q45 should be equal to what? Q34 minus V B4 Y sub 4, and if we do the calculation, this should give you, I mean, you can use your common sense. Here's the force. The vertical force is only going to be acted by the vertical members, no? Okay? So by symmetry, if you want, by logic, if this is 0, you can do the math, but I can bet you that this term is going to be 0. Okay? I mean, we can go and check on the MATLAB, but it should be 0, Q450, okay? You see only the one on the vertical members. We react the force. Now, so we do 2, 3, 3, 4. Okay, now let's do, if you want 5Q25, so Q25. So Q25, it will be equal to what? 0 on this side plus 0 on this side. So because we have Q12 is equal to 0, so this will really be Q12 plus Q23, but both of them are 0. Okay, so 0 and 0 minus V times B2 Y2 divided by IXX. Okay? So this will be, so this is 0 minus V over IXX. Is the same thing, no? Okay, well, good here. So this is 0 minus this, and this is going to give you that Q25. I mean, you can do the math, but it should be what? I mean, just using your common sense, this one should be twice, no? B was 650 for this one is 1300, no? So it should be twice that one. So 45.5 times 2 is 89, so it should be minus 89. So if you want, we kind of finish cell 1 and 2. So this is the common web. Now we do cell 2 will be Q56. So here we need to be careful. Q56, I mean, will be equal to what? Will be equal to Q45 plus Q25 minus V over IXX B5 Y of 5. And this one, the math should also give you 0. Okay, if you want, you can go and check, but Q56 should be equal to 0. We can go and check on the MATLAB again. Q56 is equal to 0, and this is expression over here, you see? Q45 plus Q25 minus Vy, I write exactly the same thing, okay? All right. So this will give you 0. Now we go to another vertical element. So this one should have a value, no? Because it's if you want, is one of the members resisting the shear force on the vertical direction. So Q61 will be equal to Q56 minus V over IXX D6 Y6. So this one, because Y6 will be equal to minus 125, will be negative, we'll have negative, negative. This will become positive, and you have Q61. That one is equal to 44.5, okay? The same thing as on the other side. Okay, and we know that Q12 is 0. So if I do a little summary of the results over here, so let's see what we have over here. Will be 1, 2, 3, 4, 5, 6. So if we do the calculation, we have what? Here 0. Here 0, because that's where we have the cuts. Here we have 0 and 0, because again, the force is only on the y direction, so only the vertical members will restrain the vertical force. Okay. All right, so now, this is the part that is, I think, complicated. That's where the error can become. You can get errors. So it's different ways to do this, but let's see, Q34 really is going up. So this will be 44.5. Now, Q25 will also be going up. I mean, the shear should be going up, okay? This one is equal to 89, and this one should also be going up, equal to 44.5. Okay? So now let's see, how did I plot it on the previous figure? How did I do the Q's going clockwise, counterclockwise? I did them going counterclockwise, okay? So we have them over here. So we have here Q1. And now Q2. Okay. Okay, so now we know in the procedure that in order to determine Q1 and Q2, we need to have two equations. Okay, so to determine Q1 and Q2, we need two equations. All right, so the first equation, we're going to get it from what? That we know that the angle of twist of cell 1 needs to be equal to the angle of twist of the second cell. Okay? And the expression for the angle of twist, the general expression for the angle of twist, I'm going to have to go back and check, but I think it's 1 over 2 AG. Let me go and check because 1 over, let's see what would that be, 1 over 2 AG, and then you need to go the integral of the Q over T. Okay. 1 over 2 AG, and then you go around the circumference of the Q over TDS, okay? All right, so let's do the first one. Let's do d theta dz1. So this will give you the first equation, okay? Okay, so this one will be equal to what? We know it's 1 over 2a, the area of the first cell, g, everything the same material. And before I forget, the area of the first cell will be equal to what? The length, this one, which is 500 times 250, no? Okay? It's on the code. And now we need to go do here. So we're going to do the summation of all of them. So hold on one second. Okay, and as somebody just mentioned in this problem, the t is constant, so we could put it outside over here. All right? So now, what I did actually to break it a little bit differently is that I said, okay, the Q1, let's say that is positive going counter, we're going to assume the angle of twist counterclockwise, okay? So Q1 here will always be producing a positive angle of twist. All right? So what I did on this one, I said there will be Q1. I just worry first about Q1 times what? I will have S23, which is, I think it's 500, no? So I did 500 plus 34, which is 250, and basically go all around, plus 500 plus 250, no? This will be the DS, no? For that term. So I go all around. All right? Now I just saw Q23, we know is 0. Now, what would be the effect of this 44.5? Will it be positive to do the angle of twist to be clockwise or counterclockwise? It will go clockwise, no? So it will be resisting the motion. So it will be minus, here I will put minus 44.5. And this one, what is the length for this one is 250. Okay? Now, in here, I don't have anything. Okay? And now I have the 89. The 89 is going to make it go counterclockwise. So that should be an effect to be positive. So it should be plus 89 times 250. And now we don't have to forget here this Q2 on the other side. We'll have a Q2 that will come this way, and here will be going down, no? Yeah? So that's going to produce an angle of twist what? Positive or negative for that segment here? It will make it go clockwise, no? So that will be negative. So it will be minus Q2 times 250. All right? And I can close over here. Okay, so after doing the calculations by hand over here, we find out that this is 1500 Q1. This is easy, minus 250, and these two terms. Actually, you see this one is half of this one, no? So we can just do 44.5 times 250, and that gives us 11,125. All right, to give some numbers over here. So now, similarly, now we're going to do d theta dz for the second cell will be equal to what? 1 over 2a2 gt. And here I've kind of do the same thing. So I'm first going to look at the effect of the Q sub 2. So what can I put? I can put Q sub 2. And I do the same thing. I'm going to go all around this one. So it should be 500 plus 250 plus 500 plus 250, okay? As expected. So the same as before. So I do the Q2 here. And now, what did I do here? Now we can do the other one. So now, what would be the effect of this 44.5? It will be also to go counterclockwise. Okay, so over here, sorry, you see I did a mistake. The distance here, 1, 2, 2, 5, 5, 6, 6, 1, they're all the same. They're all 250. So it should be as well 250. Okay? Now, and they're still going to go counterclockwise. Now, let's say we start here by Q16 or 61. The effect of this one will be to make it go counterclockwise. So that would be positive, no? Plus 44.5 times 250. And that will be positive. Now, the 89 this time is going to make it go clockwise, huh? So it should be negative. So minus 89 times 250. And finally, we need to look at the effect of the Q sub 1 over here. So the Q sub 1 here will be going up, is going to make it go clockwise, no? So it should be minus Q1 times 250. All right, and this is going to give us d theta dz of 2 equal to what? 1 over 2 A2 GT times minus 250 Q1, and then this one will be plus 1000 Q2, and now this should be now the minus, I think this will be the same thing, 11,125. Okay, so let's check very quick the MATLAB code if I've been kind of doing the same thing here or not. So let's see, this will be the first one. So I did this one all positive. So let's check minus Q2 S25 over T25 minus 34 plus Q25. So that looks about the same. You see I put absolute value. So this is S12 minus Q1, okay? Plus 61 should be that the 44, okay, positive, minus the 91 should be the middle one. So that looks to be about the same. Let's see if I did any error on the inputs. 2. Okay, so I think one should be half of the other one, I'm pretty sure. So A1, no, yeah, it's half, no? So A2 is half. Is that possible? Yeah, it's half of the other one. Or not? Yeah, that's about right. So it's half. Okay. So we know, so A1 is twice, so A2 is half. Okay. So just trying to go here. So now, the first equation, we're going to get it doing what? We're going to equate the two angle of twist over here. So guys, so you see that even though I do the MATLAB code, I still need to show the work, no? Okay? All right, so now I do the angle of twist of the first cell needs to be equal to the angle of twist of the second cell. So we have 1 over 2 A1 GT times 1500 Q1 minus 250 Q2 plus 11,125 equal to 1 over 2 A2 GT of minus 250 Q1 plus 1,000 Q2 minus 1,125. Okay, so over here we can cancel these two, the G, the T, G, T. And then what do we know? We know that, I think is A. So from the picture, looks like what will be A1 should be 2 A2. So A1 A1 equal to A2. So this will give us what? So we simplify everything by 2A2. We eliminate the A2. This will give us half of this. So this will give us 750 Q1 minus 125 Q2 plus, let's see, 125 divided by 2. 11125 divided by 2 will give us 5,000. So I just do the half, would be easier than 11125 divided by 2. I think it's easier than writing that. And this should be equal to minus 250 Q sub 1 plus 1,000 Q sub 2 minus 11125. Okay, so let's see. If we do this, what are we going to get? If I move everything to the left, it would be 1,000 Q sub 1 minus 1,125 Q sub 2. And then we get, so we get the 11125 divided by 2 plus the 11125. So whatever that is, so it's 1.6688 10 to the 4th. Okay, if I didn't do any mistake. Equal to 0. And this should be our equation 1. All right, so now we need to find the second equation. So in order to determine the second equation, what do we need to do? We do summation of moments of the external forces need to be equal to the moment created by the internal forces. Okay? So let's first check if, let's see if you see, because I'm going to give you the result from that code. So do you see anything that looks bad over here from what we wrote on the notes? I think it's about the same. Let's see the areas, A1, A2, G. I just put here T's in case there were different thicknesses. Okay, I tried to make it general, but it looks about that. Now we need to take the moments about the lower point. So I took here 0.5. So I did that yesterday in class with you, but I didn't check anything, okay? So about 0.5 we have done, okay. All right, so let me just redo the figure here. Oh, 104. I have two 104s now, so okay, hold on one second. This would be 105, 106. So I was looking for which figure, this one here. Okay. So I'm looking more or less for that one. So we have 1, 2, 3, 4, 5, 6. So we're going to be taking moments about this point here, 0.5. All right. And then what do we know here? This is 0, 0, 0, 0, 44.5, 89, 44.5, Q1, Q2, 250, 250, 500. And I forgot maybe something extremely important is that what is the force applied? At point 2, no? So why is the reason that I selected 0.5 in this case? I mean, you could select any point, but just because the moment created by the external force would be equal to what? 0, okay? So let's say here I write down, so summation of moments, external about 0.5, assuming positive counterclockwise, will be equal to 0, no? Okay? And now we do summation of moments internal about 0.5. So what are we gonna have? So let's start by cell 1, okay? Let's start by 3, 2. What is the value of the shear flow over 2 and 3? It will be Q sub 1, no? Yeah? So we have Q sub 1. What would be the arm? It will be 250, okay? Now, let's go around. What would be the moment? Let's do all, let's do one by one. Okay, we can change it, but let's do this one. Now, what would be 3, 4? The 3, 4 here will have the 44.5 will be creating a clockwise moment. So that should be negative, so minus 44.5. What would be the arm? 500, no? But now let's not forget that also between 3 and 4, we're gonna have Q1. Yeah? So now Q1 will be creating a counterclockwise moment. So plus Q1 times 500. And now Q45, the moment will be 0, no? Because going to the point, and Q25 will also be 0. So here we took care of everything around cell 1. All right? So now let's go to cell 2. So let's start by 1, 2. 1, 2, we have, this is 0, but we have a Q2 going to the left. So that will create a counterclockwise moment, no? So it will be plus Q2. What will be the arm? 250. So 1, 2, we have done 1, 2. This one will have 0. 5, 6 will be 0. Now, 1, 6, what will we have? We have the 44.5 will be creating a counterclockwise moment. So plus 44.5 times what? The arm will be 250. Okay, that distance here. And we're also going to have the Q2 plus Q2 times 250. Okay, so here again, one of my silly mistakes. Here, this is the shear force. This is not this is the shear. This is not the force. Okay, so let's just redo again. So let's see what I forgot to multiply here by. So let's start. This one we did Q1. So it should be 500, no? This is this one here. Now this one was this 44.5, so we need to multiply here to have the force by 250. So this one is this one. Now we have the Q1 is also the effect of this one going down. So this one should be also be multiplied by 250. Now, when we do here, I'm going to do it down this time or under. So this is the Q2. We started by 1, 2. So it should be 250 here. Everything should be 250. So this is 250. This one is also 250. And now this will be the Q2 going across this one will also be 250. So let's see what I did on the maple, see if you see anything different. So what did I do here? I did minus AB34, okay? S34 times 61. 61 we did positive, we have it positive, plus Q2, both of them positive. Oh, but Q and Q1, both of them positive. Okay, check those distances. I will give you this code. You can go and check it. So now, let's see if I can do equation 2. So it should be equation 2. So let's see, where is that? Okay, so let's see if you can make it pretty here. VPA AQ2. Doesn't look pretty at all. So let's put here this value about 250,000 Q1. Let me write it down. So this will give you minus 250,000 Q1 minus 125,000 Q2 plus that big number plus 278,1250. Okay, I'm gonna put this can be equal to 0. Okay, so what does that mean? That means that now from the previous part, we had this equation by doing the same angle of twist. This will be our equation 1. And now we found our equation 2. So that means that we have two equations with two unknowns, Q1 and Q2. So solving. The system of equations for Q1 and Q2. I mean, guys, you are trusting me here a little bit too much on this code, huh? I did it yesterday very quick, so that's what I was hoping. All right, so let's see. So I use this in MATLAB, this command here, solve. So let's see. So, I mean, I'm going to give you this code, but it's up to you to check it. So we get Q1 equal to 2.567. .567 and Q2 equal to 17.115. And this should be newtons per millimeter. Okay, so, well, we're not going to finish. So the final shear distribution is what? Again, the best thing is to redo the figure. Where we have 1, 2, 3, 4, 5, 6. We know this is 44.5. 89. 44.5. This is 2.567. 17.115. So let me go and check the MATLAB code very quick, because this is the part that I didn't even check yesterday. So I didn't even look at it. So Q12 will be just Q1. Huh? Okay, no, will be Q2. Y minus Q2. Okay, so you see, so it should be plus Q2, I guess. Q23 will be equal to Q1. Okay, plus Q1. Q34 should be equal to absolute this one minus Q1. Okay. Q45 will be equal to Q1. Positive. Okay. Q56 should be equal to Q2. Y minus plus. Q61 should be equal to the summation of these two. Yes. And this should be equal to, and 1, 2, what did I do? Okay. And the common web should be equal to absolute Q25 plus Q1 minus Q2. Okay. So let me run this, and we can check with the sketch. Okay. But basically, what are we going to get? We're going to get that Q12. So if I do the figure here, let me just redo the figure. I do it a bit bigger. 1, 2, 3, 4, 5, 6. Okay, so let's see. If we look at the figure here, what will we have? This one should just be equal to Q sub 1, which is 2 point, no. We're looking up, okay. So Q12 is this one. Let's start by this one. Should just be Q2, which is 17 point, let me just say 17.2, okay? I'm gonna simplify everything. 17.2. 17.115, but it doesn't matter. Then Q23 should be equal to Q1, which is 2.567, let's say 2.6. Q34 should be equal to the 44.5 minus the 2.567, which is 41.9. The 4.5 should be equal to the 2.567, the 2.56. The 5.6 should be equal to the 17.2. Let's see if that is what we get. Yeah. So 5.6, 17.2. And 1.6 should be equal to the 44.5 plus the 17. 61.6. And then the center one should be 89 plus 2.567 minus 17, which gives, so it should be Q25, 74.5. All right, guys, so over here, you see I forgot the material properties. So this one is Q over G T. Okay. All right, so let's go back here. All right, page 108, and we're almost done. So now, so the deformation due to shear, which is due to the torsion of this cross section, we have the expression to be equal to what? So how do I call that expression? So Q to shear to be equal to the interval 0 to L of Q over GT partial Q partial V ds. And now this is dz. Okay, so remember that Q generally is given by what? It's given by minus V over I XX, or let's say B of I, Y of I. Okay? So if this is this, what would be the partial Q? partial V will be equal to minus 1 over Ixx B sub I Y sub I. So if I substitute over here, we have what? Q2 shear is equal integral 0 to L across the cross section of minus V Pi Y sub I over GT times minus 1 over, oh, I forgot the Ixx here. Ixx B sub I Y sub I. And this should be dz. Okay, so now we agree that this term over here will be Q because it's exactly equal to this one. Yes, and this one kind of will be proportional to Q over V, no? Yes, okay. So at the end, I could just rewrite this expression over here. Will be equal to 1 over G times V, the shear force times T. We could put the T over here as well. This is constant. Integral 0 to L. And this will just be the Q delta Q over V ds dz. Okay, or this, actually I should have done it a little bit faster. It should be 1 divided by G Vt integral 0 to L of the, I'll finish in 2 lines, okay? Okay, Q square, so this will be Q over V, so it will be Q square ds dz. So basically, the Q2 due to shear will be equal to 1 over G Vt integral of what? Let's say Q bar 1, 2 square times S12, which is how much? Whatever, S12, which is basically probably what I have here on the MATLAB. Q1 squared S12 plus Q bar 23 square plus S23. Okay, and you keep adding all the terms to the end. All right. dz, and this will give you that Q. So the deformation due to shear is equal to 2.54 millimeters. Oops, sorry for that, 2.54 millimeters. So that finally we can say that finally the total deformation so Q2 is equal to Q, what did I call it? Q2 bending plus Q2 shear is equal to what? So the 1-2 bending was equal to 21.17. 21.17. So the total deformation of Q2 is 23.61 or 0.6. That's what this would give us. 23.7, sorry. 23.7 millimeters. Okay, so I just want to mention that. So now if I go very quick and open, I think it's this one here. I think that's the model. And I look at the deformation, F5. So the Y deformation. Okay, I can just put the, if you want the contour, and we can just look at the value here. Okay, 24.48, we got 23.7, no? Okay, is about the same range. Okay, so guys, I hope this is gonna help you, but please check the calculation with the MATLAB, okay? Because we just did it live. It's not that I had worked it out before. That MATLAB code, I just did it very quick. And if you find something wrong, let me know.